The first heartbeat. How lifeless matter learned to copy itself. 4 billion years ago, this planet was sterile, rock, water, and gas, and then something began to copy itself. It is the least understood event in the history of the universe, and every one of us is its consequence. Chapter 1. The hardest question. How does non-living matter become alive? It is the oldest question in biology, and the only major one still unanswered. We have theories, we have chemistry, we do not have the answer. Life does three things. It holds information, it copies that information with small errors, and it captures energy from its surroundings. A crystal grows, a flame consumes, neither does all three. The early Earth had no oxygen, no ozone layer. Ultraviolet light struck the surface unfiltered. The moon hung far closer, raising tides hundreds of meters high. This was the nursery. The oldest widely accepted traces of life are 3.5 billion years old. Layered mounds built by microbes called stromatolites, which means life appeared astonishingly early, almost as soon as the planet cooled. Here lies the deepest problem. In every living cell, proteins are needed to copy DNA, and DNA is needed to build proteins. Each requires the other. So which came first? Science split into two camps. Replication first, something that copied itself, and only later learned to eat. Or metabolism first, a self-sustaining network of reactions that only later learned to remember.
Chapter 2. The Clay Hypothesis.
In the 1960s, a Scottish chemist named Graham Cairns Smith proposed something that sounded absurd. The first living things on Earth, he said, were not made of carbon. They were made of mud. His metaphor was a stone arch. An arch cannot stand until the final stone is placed, so it must be built upon a wooden scaffold. Then the scaffold is removed and vanishes. Life, he argued, had a scaffold, and we threw it away. Clay is not dirt. Clay is a crystal, sheets of aluminium and silicon, stacked like the pages of a book, each layer a fraction of a millionth of a meter thick. Crystals grow by copying the layer beneath them, and they copy their flaws. A defect in one sheet is reproduced in the next and the next. Cairns Smith saw what this meant, a pattern that copies itself, with variation. Water breaks the crystal apart. Each fragment grows again, carrying the same pattern. Copying, variation, and the fragments that grow fastest become the most numerous. That is natural selection, in mud, without a single gene. Then came his boldest claim. Organic molecules stuck to the clay, ordered by its pattern. At first they served the crystal. Eventually they became better replicators than the crystal itself and took over. He called it genetic takeover. The idea was elegant. Clay is everywhere. It concentrates molecules on its surface. It shields them from ultraviolet light. It even sorts them by shape and charge. The early Earth was covered in it. One clay in particular drew attention, montmorillonite. It is soft, layered, and chemically restless. And in the laboratory, it turned out to do something no one expected. In the 1990s, the chemist James Ferris showed that montmorillonite could take single RNA building blocks and link them into chains up to 50 units long, without enzymes, without life, just clay, water, and time. There was more. In 2003, Jack Szostak's laboratory found that montmorillonite also accelerates the assembly of fatty membranes into tiny bubbles, and that RNA can end up trapped inside them, clay building the vessel. And yet, half a century on, no one has ever demonstrated it. No clay crystal has been shown to carry meaningful heredity. No genetic takeover has ever been observed, in any laboratory even once. The scaffold was beautiful, but it may never have existed. Today, almost no researcher believes the first organisms were clay, but almost every laboratory studying the origin of life still uses montmorillonite. The theory failed, the mineral stayed. In science, that is not a small legacy. Chapter 3. The Primordial Soup. In the 1920s, working independently, a Russian and a Briton reached the same conclusion. The early ocean, rich in simple molecules and charged with energy, could have brewed the ingredients of life. Haldane called it a hot dilute soup. In 1952, a graduate student named Stanley Miller sealed water, methane, ammonia, and hydrogen in glass and struck it with electric sparks to mimic lightning. Within a week, the water turned brown. The brown sludge contained amino acids, the building blocks of proteins, made from nothing but gas, water, and electricity. The results stunned the world. It seemed that life's ingredients formed almost effortlessly. But there was a flaw. Miller assumed an atmosphere rich in methane and ammonia. Geologists now think the early air was mostly carbon dioxide and nitrogen, far less reactive. Repeat the experiment with that mixture, and you get almost nothing. The story has a coda. After Miller died, sealed vials from his forgotten volcanic experiments were reanalyzed with modern instruments than he ever knew. Volcanic settings, it turned out, worked better than open sky. And here's the trap. Miller made ingredients, not life. Amino acids form easily across the universe. Assembling them into something that copies itself is a problem of an entirely different order. Chapter 4. Life Came from the Stars. There is another possibility, older and stranger, that life or its ingredients did not begin here at all, that they fell from the sky. In 1969, a meteorite broke apart over the Australian town of Murchison. Inside, scientists found more than 90 amino acids, most of them unknown to life on Earth. This rock had formed before our planet. It went further. In 2022, all 5 of the nucleobases used by DNA and RNA, the letters of the genetic code, were confirmed in meteorites. The alphabet of life exists in space. But panspermia has a weakness that no discovery can fix. If life came from elsewhere, then it began elsewhere. The question is not answered. It is only moved somewhere colder and further away. Still, it taught us something profound. Organic chemistry is not rare. It happens in comets, in dust clouds, between the stars. The universe is stocked with the raw material. What is rare is the assembly.
Chapter 5. The Fire of the Abyss.
In 1977, a submersible called Alvin reached the seafloor near the Galapagos. Its lights found something enchipped of rock, gushing black scalding water, and swarming with life, in total darkness. These creatures do not depend on sunlight. Bacteria at the base of the food chain feed on hydrogen sulfide from the Earth's interior. Life, it turned out, can run on chemistry alone. The chemist Gunther Vectorshauser proposed that life began on the surface of a mineral, iron pyrite, fool's gold. Its charged surface could grip small molecules and drive them to react, building a metabolism before any genes existed. This is the metabolism first camp. Life did not begin with a copier. It began with a self-sustaining cycle of reactions, a fire that keeps itself burning, long before it learns to remember how. The evidence is inside you. Deep within your own enzymes sit clusters of iron and sulfur, atoms arranged exactly as they are in minerals. They are the oldest components of the cell, fossils of a mineral origin. Black smokers, however, have a problem. Their water exceeds 300 degrees, and it is acidic. Molecules as fragile as RNA are destroyed there in seconds. Whatever life began, it did not begin in that inferno. And so the search continued. Until, in the year 2000, a different kind of vent was found, quieter, gentler, and far more promising.
Chapter 6. The White Towers.
It is called the Lost City, a field of pale carbonate towers, some 60 meters tall, rising from the Atlantic seafloor. They are not volcanic. They are made by rock reacting with water. The process is called serpentinization. Seawater seeps into the Earth's mantle rock, and the rock reacts, swelling and cracking, releasing hydrogen, heat, and alkaline fluid. No sunlight, no volcano, just rock and water. Cut one of these chimneys open, and you find something extraordinary. It is porous, riddled with microscopic compartments, each the size of a cell, separated by thin mineral walls. A stone honeycomb. Now the crucial point. On one side of that thin wall sits alkaline fluid. On the other, acidic ocean. That difference in charge is a natural proton gradient, and a proton gradient is exactly how every living cell on Earth makes its energy. Yours, right now. Michael Russell, William Martin, and Nick Lane argued the case. Alkaline vents provide carbon, hydrogen, minerals to catalyze, compartments to contain, and above all, a free source of energy in exactly the form life still uses. Every living thing descends from one population, the last universal common ancestor. In 2016, researchers reconstructed Luca lived without oxygen. It was fond of heat. It fed on hydrogen and carbon dioxide. But be careful. Luca was already a cell, with genes, membranes, and a genetic code. It stands late in the story, not at its beginning. Behind it lies a darkness we have not yet entered.
Chapter 7. The RNA World.
Return to the deepest problem. DNA needs proteins. Proteins need DNA. Unless there existed a single molecule that could do both jobs at once, store information, and act upon it. That molecule is RNA. Chemically, it is DNA's fragile cousin. But unlike DNA, RNA folds. It twists into shapes. And a shape is what allows a molecule to grab, to cut, to build. In the 1980s, Thomas Sesh and Sidney Altman discovered RNA molecules that cut and splice themselves, with no protein involved. They were catalysts. They called them ribozymes. It won them the Nobel Prize. And then the decisive evidence. The ribosome, the machine that builds every protein in your body, was mapped. At its very heart, where the chemistry happens, there is no protein at all. There is only RNA. The ribosome is a ribozyme. This is not a theory about the past. It is a fossil, working inside every cell of your body, right now. The oldest machine on Earth still runs on RNA, because it was built before proteins could build anything. In 1986, Walter Gilbert gave the idea its name, the RNA world, a stage in which RNA molecules copied themselves, mutated, competed, and evolved, long before DNA, long before proteins, long before cells. For decades, it had one crippling weakness. Nobody could make an RNA building block from scratch. Sugar and base simply refused to join. Without that, the RNA world was a house with no foundation. Then John Sutherland stopped trying to join sugar and base. In 2009, he built the nucleotide by a different route entirely, from simpler chemicals, and it assembled itself. The impossible step had been an imaginary one. His later work went further. From hydrogen cyanides, sulfur, ultraviolet light, and metal catalysts, a single connected chemistry yields the precursors of nucleates, amino acids, and lipids all at once, genes, proteins, and membranes, from one pot. Chapter 8. The First Cell. Fatty molecules in water do something remarkable on their own. They close into hollow spheres. Feed them, and they grow. Shake them, and they divide. No genes required. A container, forming itself. David Deamer showed that shallow pools, drying under the sun and refilling with rain, force molecules together as the water leaves dry. Each cycle builds longer chains, the tide, or the sun, doing the work of an enzyme. And here the story turns. These are not 9 rival answers. Clay concentrates and catalyzes. Vents supply energy and shelter. Pools drive polymerization. Membranes contain. RNA remembers. The question was never which one. It was how they combined. So where does the evidence stand? Most researchers now accept that an RNA world existed. It is the strongest hypothesis we have because it is the only one with a fossil still running inside us. Where it happened, vent, pool, or shore, remains fiercely debated.
Chapter 9. What we still do not know.
One fact should keep us humble. In 70 years of trying, no laboratory has ever made life from non-living chemicals. We have built the parts, we have not started the engine. And the deepest question remains open. Was this a fluke, a single accident in a sterile universe? Or is chemistry, given rock and water and time, simply inclined to wake up? We do not know, but we now know where to look. 4 billion years ago, on a sterile rock, chemistry crossed a line it has never crossed again. Everything that has ever lived, every forest, every whale, every one of us, is the still unbroken continuation of that single moment.
Thank you for watching.